Hello folks, and welcome to this lesson on calculating first ionization energy. By the end of this lesson, you should be able to calculate the values of first ionization energy from spectral data that gives the wavelength or frequency of the convergence limit. So before we talk about calculating ionization energy, let's do a little bit of a recap on the relationship between energy and light. So here we have a look at the different types of electromagnetic radiation that you can have, from radio waves to gamma rays with visible rays somewhere in the middle there. All of these different types of electromagnetic radiation have the same speed, but they do have different wavelengths from each other and also different frequencies. Now, electromagnetic radiation is based on waves, and so a wave is always going to have various different repeating units. Now, in terms of these repeating units, the wavelength is going to be the length of one repeating unit in space, and so typically they're measured in meters or something of that sort, and your frequency is how many repeating units you have in a unit of time. And typically that unit of time is going to be 1 second. Now, in terms of the relationship between frequency and wavelength, the bigger the wavelength, the smaller the frequency you have. Or, if we're talking about the relationship itself, there is an inverse relationship between frequency and wavelength. Now, if we take all of that and put it into an equation, we get C equals lambda F, where C is the speed of light, typically in a vacuum, lambda is a symbol for wavelength, and F is used for frequency. The value of C that you are going to use is typically 3.00 times 10 to the power of 8, and the units for that is meters per second. And so whenever you're doing these calculations, you have to make sure that you're making all the units match up. Otherwise, any canceling that you want to do is not going to happen properly. So we have our wavelength, and again, this needs to be converted into meters for the question to work properly. That being said, a lot of the wavelengths that you're going to use are going to end up being in nanometers, mostly because that's where it's visual, and so we can see that information. And so you have to make sure that you're changing your nanometers into meters whenever you're doing any calculations. Now, frequency is going to be 1 over second. 1 over second is also known as hertz, so that's capital HZ. And so if you have hertz, you don't really need to do any unit conversions. You might want to change the hertz into 1 over seconds just so that it's easy to keep track of those units when you're problem solving, but they're basically the same thing. So let's talk about the relationship between all of this and energy. So while electromagnetic radiation is always going to have the same speed within a specific medium, the amount of energy that any type of electromagnetic radiation is going to differ depending on what you're looking at. If you think about this logically, radio waves are all over the place. We have radios going on at all times, but you never hear of anyone getting hurt by them. As opposed to X-rays and gamma rays, where they do have issues and they can harm people. You have warnings where pregnant people are not supposed to undergo X-rays in fear of harming their fetuses, and so on and so forth. And also ultraviolet rays or UV rays are linked to cancer and things like that. So the reason why some of these radiations are associated with not being harmful and some of them associated with being harmful is because of the fact that they contain different energy. Based on what we've just talked about, you might be able to make the conclusion that wavelengths that have shorter wavelengths have more energy, or, on the same train of thought, if you have a radiation that has a higher frequency, that has more energy to it. Now, in terms of scientists and the work that they've done, the equation that we're going to use to tie this all together has frequency in it and not wavelength. So we have energy. This is Planck's constant. and it will be given to you in any evaluation situation, and of course F is your frequency. Now, while frequency is a very useful value, a lot of the times when we think about radiation, we associate the different types, or we're more familiar of looking at them in terms of their wavelengths rather than their frequencies. And so a lot of the times in the questions that you use, you might be given wavelength, which then you need to use to calculate energy, or vice versa. Now, if you remember what you've learned about emission spectra, you get these bands from when excited electrons go back down to a lower energy level, and while it's going back down, it releases energy as electromagnetic radiation. The fact that the distinct bands exist is because those energy levels have distinct amounts of energy associated with them. Now, if you also remember, once you get to those higher frequencies, those bands get closer and closer and closer together. They converge with each other. And after that, we do get to a point where you don't have distinct bands anymore, but you just get all of the wavelengths after a certain point. That point after which you always get all of the colors, that's referred to as a convergence limit. So why does this happen? Well, when you're inside the atom, all of your electrons are only going to have specific amounts of energy. So any drops that will happen will always be specific amounts of energy. They will be specific frequencies, specific wavelengths. But the thing is that once you get outside of the atom, those electrons might have any amount of energy. And so when it goes from the outside to the base level, all of these possibilities are going to show up in your emission spectrum. So the convergence limit ends up being the lowest amount of energy an electron from outside the atom can come into the inside of the atom. So this means the minimum amount of energy that you need to take an electron out of an atom is going to be where that convergence limit is. So here's an example of a practice problem that you might see related to this topic. Pause the video and see if you can figure it out. Alright, so the question is asking, when you are given this energy, calculate the wavelength of convergence for the sodium atom spectrum. So we're going from energy to wavelength. The two equations that we know of are E equals HF, and also C equals F lambda. We are given this particular value, and it will give us frequency, but frequency is not what the question wants. It wants wavelength, so we're going to need to use this second equation to get that lambda value. So if we take the values and put them into our equation, we need to find out what your frequency is. Now, something that you want to keep in mind here is that this value is given in kilojoules, but Planck's constant as given to you is in joules. So we are going to have to do a unit conversion to make sure that we can solve this problem properly. So once you take those values, do the unit conversion, isolate for F, you're going to get this. And then you're going to get a value of 7.4811 times 10 to the power of 38. And then let's take a look at our unit. Our joules cancel out, but we're left with 1 over mole, or mole to the -1, second to the -1. Now this gets us part of the way, but the thing is that frequency shouldn't have moles in it. And so the thing is that this energy that we get is for 1 mole's worth of sodium, but we really only want it for one of those wavelengths. So we have to take this and figure out what the frequency it is for one of these particles. So we need to get rid of the moles somehow. So 4 moles, and to get rid of that, we're going to use Avogadro's number. We have to divide it by Avogadro's number, because remember, that is 6.022 times 10 to the 23 per mole. So we're going to be dividing it. And so that will get rid of our moles, and that will give us our frequency. So once we have our frequency, we now need to find out the answer to this question, which is wavelength. So we're going to take all this and substitute it into that other equation. And once we do that, our seconds will cancel out, and we will get an answer of 2.41 times 10 to the power of -7 meters. Now in terms of our sig digs, we have 3 sig digs basically in all of our values, so our final answer is also going to have 3 sig digs. Now, if the question asks for a different unit, you can do so, but it's not, so we're going to leave it at that. That's the end of this lesson. I'll see you next time.